We'll just start the webinar in a minute. All right. Can you see my screen, all of you?
Yes, Karthik.
Vishma, yeah.
Yes, Karthik, yes.
Okay. Good evening, ladies and gentlemen. Thank you so much for joining us on yet another webinar from Ansett. We do this webinar every Thursday, the first Thursday of every month. Unfortunately, we couldn't make it up last week, primarily because we were all held up in all these year-end deliveries. I'm sure all of you must be aware of going through the same process like us. So once again, thank you for holding on and joining us on this Thursday. So today we will be focusing on runtime environment. And quick introduction about Ansett. We are primarily an automotive service provider company working in this field from 2007. 15 years we've been working in automotive, providing custom tool development for various automotive development processes like development, testing, etc. We do some training, we do consulting services, we do a lot of customization on automation as well, on a lot of processes and things like that. That's a quick background about Ansett. And like all these years, we've been working exclusively with OEMs, tier ones, semiconductor industries, all on the automotive space. And I'm Karthik, and I head the research division of Ansett. So today we are going to spend some time trying to understand on the runtime environment. So for members who have, like, say, already gone through our previous webinar on runtime environment, we have talked about how do we construct an application software component. We've actually shown you this entire virtual function bus level, where we demonstrated how we construct a virtual function bus. So what are the components and designs that goes into the virtual function bus, and what are all those things, etc. And we also, like, say, discussed about some internal behavior there, which we call RT level, and some implementation. So today our webinar is going to be a little different. So I'm not going to talk more from a design perspective that is discussed. I'm going to talk more from a code perspective. Okay, so what do I mean by, like, say, certain terminologies? What do I understand? What are the equivalent C codes of those terminologies? What does a runtime environment in C mean? How is it going to happen? What is the responsibility of the runtime environment? How is it working? And more things like that. So that will be the whole idea of today's agenda. So we're not going to talk more from a design perspective, from a tooling perspective. I would like to talk more from an implementation perspective, where I will call the software component internal behavior, etc. Okay, for members who find it, like, say, certain terminologies, what we have also carefully done is we have made sure that whatever topics that we have addressed, whatever topics we are talking about, have been already addressed in our previous webinar. Those terminologies have already been addressed in our previous webinar. So if at all you feel some kind of a challenge, you can always refer to that older webinar. So today we're going to spend time on the runtime environment. So the runtime environment is the heart of the AUTOSAR architecture, serving as an interface between the application software component, where your entire logic is sitting, and your BSW stack, which is responsible for talking to the microcontroller or the underlying board. All right. So so the runtime environment is responsible for bridging the gap between these two guys. So that's the basic idea. So these are certain things that we have done. We have seen we've created an application software component. We have created codes. We have created interfaces. We have created assembly connectors, okay, to interconnect the port and interface, okay. So all those things, and then we have done also, like say, created some runnables, and we have seen some high level. So today what I want to show is I want to write all these things, the equivalent of all these guys in a C perspective. So let's spend, like say, a few minutes on that, and then we will move forward, okay. I have my notepad, so I'm just keeping both my notepad and my software component, okay. My this thing. So when I say create an application software component, what does it equivalent mean? See, it's nothing but a .c file that we create, okay. Let's say, for example, my .c file is called okay, some pwm.c file, just to give you a, all right. Or to keep it very simple, we'll just keep it interior light .c file, something like this. Okay, so when I say creating an application software component, it actually creates this. This is what we mean by application software. There are, like say, different application software components. We have a sensor actuator. We have, like say, application software component. We have a calibration software component. We have mode switch components, memories, so many types of software components. But generally, it's a .c file. It's a .c file, most of it. Okay. So now we will talk about, after we create this thing, the next ideas we would have created data types. All right. We would have created data sets, and in data types we have both implementation and AUTOSAR data types. Of course, this could also be mapped with application data types. Application data types mapped with implementation data types, which in turn is mapped to AUTOSAR data types. So once we have this done, we create port interfaces. Okay. Port interfaces are nothing but in simpler terms, you could, like say, call it, like say, a structure, okay, with its variables. All right. So let's say, for example, if I create port, okay, if I create a port interface, okay, there are two types of port interfaces. One is called as a sender receiver port interface, and the other one is called as a client server port interface. All right. So whenever I create a sender receiver port interface, it's nothing but a structure. It's nothing but a structure that gets created. Okay. And let's assume I have a structure, and I have a structure, and I create a port interface. Let's assume I have a port interface struct PA, the name of the PI, LED, I'm sorry, light monitor. Okay, and I create a data type IDT. IDT maybe say light control, and I initialize this. Okay, I can initialize it later. Just create. So this is exactly what I meant by port interface. So this is what I mean by a port interface. So when I create a port interface, sender receiver port interface, it actually translates into a structure with n number of data elements, and each element of the structure in AUTOSAR is called data elements. These are called data elements. And whenever we have data elements, we have the structure created. The next structures we create ports. So ports are nothing but structure variables. Okay. So I can have, like say, different types of maybe for left light, or like say I can keep it front light, and I can keep something like say rear light as well. All right. So I could, like say, have n number of ports. So when I which are using the same port interface, okay, which are using the same port interface. So the idea is, whenever I create a port interface, I will create a structure, and the structure variables these are with n number of structure elements. These structure variables are nothing but my ports. Okay. So whenever you are connecting two ports, in your design using a assembly connector. Okay, that means both of them should be using the same structure. Okay, both of them should be using the same structure. That's the general idea. Then one other interesting thing is these days will always be connected with assembly connectors. In the C code, let's assume I have I have only one element inside the structure. Okay, I now only declare one element inside the structure. This particular element does not need a structure because a structure is usually created for elements with different data types. If I have only one data element that is declared inside the structure, then the tool will be intelligent enough to generate a code which is of type variable. Okay, so for this structure, when you see the code, you will not actually get a structure. You will get only one variable. You will actually get only one variable. So that's the advantage of the tool. Okay, so when we use a tool, the tool will be able to intelligently enough to understand, okay, this is a port interface which has been created, but it has got only one element in it. So I don't necessarily need to create a structure. I will only create one variable with some data type. Okay, so it will create a variable with some data type, IDT, light, DE, light control. So that will be it. So this is what we mean by a sender receiver interface. Sender receiver interface. Okay, and the sender and the receiver will always have a same structure. Okay, so next is we have something else which is called as a client server port interface. So whenever I see a client server port interface, the client server port interface actually translates nothing but function call and function definition. Okay, it actually translates it to function call and function definition. So the function call will be sitting in the client port. Okay. The function definition is nothing but the server port. This is my server port. Then what is my port interface? Port interface is nothing but my function prototype. Okay. So when I create a client server port interface, what I necessarily do is I can have I'm going to have a function prototype that is going to be defined. I can create one port interface, and inside that port interface, I can have n number of function prototypes. That's also possible. Okay, that's also possible. But the general idea is whenever I'm talking about a client server port interface, it's usually a function prototype that gets declared. And when I'm creating a function, it will be in some .h file. So idea is when you want to declare one function call, that will be sitting in another one.c file. Function definition could be in another .c file. So these are the two ways that they will, like, say, communicate. These two .c files will communicate. Okay. So this is the general idea of the client server interface and the port, what is it called? Sender receiver interface. So the idea here is we have talked about in our previous webinars, we have talked about sender receiver port interfaces. We have created sender ports, we have created receiver ports, we have connected all these ports. Similarly, we have created client server ports and client server port interfaces. But what we have missed out is what does it necessarily translate into a C term? Okay, so at the end of the day, it all gets translated into C code. Okay, so this is how a sender receiver port interface will translate into a C code. This is how a client server C code. Okay, so this is something that I wanted to start with because this is something that we have not covered in our previous webinar when we were talking about runtime environment. All right. The idea is that the general idea is we have, like, say, we create ports, we create port interfaces, we create n number of software components. Why is that you need to create these port interfaces, ports, and all those things? See, whenever we are talking about developing an automotive software, it's not generally one .c file. You will have n number of .c files. You need variables to be communicated between two .c files. I'll always use a class sender receiver interface where one .c file is responsible for transmitting the data and the other .c file will be responsible for receiving the data. So where the guy who's sending the data is called sender, the guy who's actually receiving the variable is called as the receiver. All right. So this is the general idea. And then we will talk about this is something that we have done. We'll talk about more about the internal behavior of software components in a little detailed way. But at this point, I would like to just emphasize on one very important thing. We create port interfaces to establish communication between two software components. It could be client-server port interface as well, which is again used to communicate between two software components. Your function call is in one .c file, a function definition could be in another .c file. So again, it is used for communication between two software components. If I'm using a sender-receiver interface, it's again used for communication between two software components, but you are exchanging variables. You are transmitting one variable in one .c file, you are receiving the variable in another .c file. So that's the basic idea. Okay. So when we talk about RTE, there are two major phases that is always there. One is called as the RTE contract phase, and the other one is the RTE phase. So again, what is the objective? What does an RTE contract phase generate? If you generate the RTE contract phase, it will create it will generate all the .c files, which I typically mean by application software component. It will create all the interface definitions, which are nothing but APIs, which are required to establish communication between the two software components. We will talk about that in a while, okay, in a little detailed fashion in some more time. But yeah, it is used to establish communication between these software components. And then we will also have a header file, okay, which will be created, which will be very specific to the component type, So the component type, if you look at it, if I have, now I've created one software component interior light.c file. So I will have one .h file for this component with .c file, which is RTE interior light.h file. Like that, it will have generate one thing. So similarly, what happens is if I have 10 .c files, each fellow will generate its own header file, and that header file will contain all the information that is required to establish communication between the application layer and the software component. So all those things will be there. So in on the high level, okay, if you look at what are the teams it will generate, if I have to put it into this perspective, I'll have one interior light .c file. I'll have one RTE underscore int light .h file. Okay, I will have all the APIs. Okay, inside that I'll have runnables. Inside the .c file. Okay. Inside the .c file, I'll have all my runnables. Okay, runnables are nothing but my functions. Okay, I'll have my functions, and inside the function, you will need various APIs to establish communication between the software components. All those APIs will be generated. So, so that is exactly what will happen in the contract phase. Okay, so we'll discuss a little more as we progress, but on the high level. So what is the RT generation phase? So RT generation phase talks about all the information that is required about the BSW software components. Okay, so there are, like say, a lot of BSW software components that will be generated. All those BSW software components will be, like say, associated with the RT generation phase, and how they are going to establish communication. All this information will be generated, more relevant to the PSW modules will be generated in the RT generation phase. Apart from that, what it will also do is it will have all your scheduling process. We will talk about that later. Scheduling, we will come to that later. How it is being deployed to establish communication between with the underlying board. All those things will be generated in the RT generation phase. And one RTE will be generated for each ECU. Okay, so you'll have only one RTE.c file on the high level. Okay, so that's the idea. When I say one RTE is generated for each ECU in the system. Okay, so it necessarily doesn't mean that for a BSW one .c file, RTE.c file will be generated, and for the application another .c file, RTE.c file will generated. No, there will be only one RTE.c file which will be generated for the entire ECU. So these are some of the contract phase files that will be generated. Of course, you'll have the RTE.c file. Okay, apart from the RT.c file, the other .h files that will be generated along with the RT.c file will be the RT._CT component type.h file, component type underscore type.h file, which will contain the types and data types and all those things. You'll have a memory.h file, and so many other files will also be generated along with your RT. So it is not just one .c file and one .h file. There will be n number of .c and .h files. I'm sorry, not .c. N number of .h files that will be generated along with this RTE.c file. Okay, so this is just an example of how the RT contract files will look like. Okay. All right. So on the high level, okay, so we've seen, like, say, we've seen the runtime environment. Let's put it into an architecture perspective and, like, say, discuss what is this runtime environment, why do we need it, and all those things. Let's say, for instance, I come up with a very simple requirement saying that I need one software component. I need to design one ECU with so and so requirement. Maybe it could be a very simple seat-eater application requirement, anything for that matter, okay, or it could be a complex ADAS algorithm, okay. So the first step the architect of the team will be doing is he'll be generating the virtual function bus, okay. So he will try to create the virtual function bus. So what do I mean by virtual function bus? In terms of C programming, what will be the virtual function bus containing? Okay, so the virtual function bus might probably contain the list of software components that will be, like, say, required to realize this application functionality. Maybe for our example, let's say I need 10 software components. In this 10 software components, I need to handle, like, say, probably some 10 structure, or I mean, like, give a number to it, 15 variables. It could be a structure variable, or it could be any variable, all right? So, or it could be an array element. It could be, like, say, totally, let's assume that there are, like, say, 15 variables that needs to be handled between these software components. We will have to define what are these variables that have to be defined, and then which we know, okay, this guy has to talk to this guy, this software component has to talk to the other software component, like that. So you have all these 10 software components, and you know which variable to pass from which software component to what. So this high level design, okay, this high level design information, when you are able to, like, say, do it, that's typically what we call it as a virtual function bus. Okay, so in terms of C programming, like I mentioned, it will be just the number of .c files. It will be the list of it will be the list of it will be the list of variables, which could be any type of variable, including structure and arrays. You declare all these variables, and you tell which software component has to talk to which another software component, which variable has to pass from what to do. And this high level design is called as what we call it as the virtual function bus design. Once we have the virtual function bus design, then we have something called as a software component behavior. With this, data types and all those things, we will not be able to do anything, but this will give you a high level picture. After that, you decide runnables. Okay, runnables are nothing but function. Each software component may have, like, say, 5 functions. Each function may be responsible for doing some work. Okay, he may be responsible for doing some work, etc., etc. So all those things are, like, say, defined in this inside the runnables. Okay, now when we have already declared these variables are, like, say, have to be, like, say, exchanged between the runnables. Okay, there has to be exchanged between runnables of different software components. So let's say, for example, I have a software component A here. Okay, I have a software component. I have, like, say, a software component. Oh, sorry. I'm sorry. I think it's not. I'm not able to draw it. Yeah, that's fine. I have a software component 1 here, and I have a software component 2 here. And I have a variable that needs to be exchanged between this guy and this guy. I will not be able to do it directly. Okay, I will have to, like, say, pass the variable only through the RTE. I will have to write it only through the RTE. So that is how it has to be done. So let me just do that for you. Okay. I'll do that in a moment, but I just want to like say highlight these topics here. Okay, so once we understand this whole high level design and we go to the RT level design, after you design the runnables, the two major responsibilities of the runtime environment, if I have to put it into very simple term, one is it is responsible for establishing communication between the software components. Okay, that means when I have two variables that needs to talk to each other, it is the responsibility of I'm sorry, you have two variables, and I have these variables to be passed between two software components. I think it's the responsibility of the runtime environment to make sure that these two variables are passed from one software component to another component. No two .c files can, like say, pass a variable directly between each other. That's one of the distinct reasons why RT plays a vital role in terms of communication between software components. Okay, so one of the major responsibilities is it has to establish communication between software components. So let me just write one small piece of code. Okay, let's say for example, I have one. I will just talk about the same interior light .c file, and let's say I have a sensor .c file. These are two software components. I have a variable. Okay, I will call this variable light. Light is the data type. Okay, light status. This is the variable. All right. Light is the data type, and light status is the variable. And I have a runnable R1. All right. And I'm going to use this runnable sensor was .c file. He needs to access this variable. Okay. So I'm going to take this. He needs the status of this light status. Okay. But how do I access it? Usually what happens is you'll put one external keyword and directly access it. It won't be possible in AUTOSAR standard. So what I need to do is I need to write this API. I need to write this light status into my RT. So I will use an API RT underscore write underscore some port name underscore data element name. And I will pass this variable. I'll have to pass this variable light status. Okay. I'm going to pass this variable. All right. So I will have my RT.c file. I have RTE underscore write underscore pp name. I'm just writing it in a crude way. It will be like, say, there will be a what is it called, and component.h file where you'll have macros which will replace this function name with another function. I'm not trying to do all those things, but I'm just trying to keep it as simple as possible for easy understanding. Okay, light data type, and let's say some data. Okay, I'm collecting this variable here, and what I will do is I have a RT underscore light underscore data. Okay, and this I will data. I will load it into my RT light underscore data. Okay, this there is RT. This is another variable I create in the RT level. Okay, this is another variable I create in the RT level. When this sensor wants to do it, okay, what he can do is he can use an extern, and actually he will have another runnable. Okay, let's say he has another runnable R2, and this runnable wants to read this data. What he will do is he'll say write RT underscore read is written right. So this fellow is reading PP name, data element, and then you pass one, like say some variable. Okay, light. Maybe says one moment. I will just put one variable here. Light status 1. I'll pass the address of this. Okay, so I passed the address of this. Now what you do is this guy, he will in this address again, it will not be the same thing, but I'm just trying to put it in a simpler word just to kind of make a life a little easy for us. Light, I need one pointer. All right. And in this flow, what he will do is he'll load the variable star light status. He will load this RT underscore light underscore. All right. So what happens? This data is written from light, this software component to RT. This guy is coming and reading from the RT.c file. Even though both these are application software components sitting in the same ECU, he will not be able to read the data directly from the application software component. Okay, so he will have to kind of read it from the RT only. Okay, so I'm not exactly writing the code, but this is something similar to this. The code will be generated. So one major even if it's a function call, okay, even if it's a function call, the function call will not be able to call the function in another .c file directly. It will call one function in the RT.c file, which in turn will call another which in turn will call a function definition, which is sitting in another .c file. So all software components will have to communicate only through RTE. Second is RTE is also responsible for scheduling of the software components. I would instead of calling it word scheduling, all runnables will be like say triggered. Okay, so in C we know that all runnables will be executed in a sequential fashion, line by line. Okay, which will not be good for an automotive standard. That's why we have like say a runtime environment and an operating system. So the entire scheduling of the runtime system will be, I'm sorry, entire scheduling of all the runnables in the software components will be done by the runtime environment. Okay, so that's the whole idea. So if I have to look at the runtime environment, if you look at the code flow, if I have to put this, okay, see, this is a runnable here. I have a runnable here. Okay, so I have a runnable here, R2. Now this runnable could be like say a periodic event. Okay, this runnable could be like say on data reception. Okay, this is an RT event. Okay, this is an RT event. And this is another nothing but an RT event. Okay, so let's say for example, how does it happen is, okay, you have your RT.c file. Okay, you have your RT.c file. All these runnables will have to be mapped to like say some OS task. So the RT events will be monitored at the RT level. So the sequence of operations is whenever the event happens, let's say for example, event is like say 30 milliseconds. Whenever 30 millisecond elapses, okay, the RTE will call the OS task. Okay, whenever, okay, I can just probably write the pseudocode. Whenever event happens, RTE calls the OS task using API activate task, and he will pass the name of the task. Maybe let's say for example task 1. Now he will like say once the event happens, the RT will call this. Now what happens? All the runnables will be mapped to this particular task, and which all the runnables which are mapped to this particular task 1, they will be like say triggered. Okay, so this is how your RTE will be responsible for scheduling. Okay, so whenever it is like say you are like say creating a RT event, please make sure that all these like say events or all these runnables have to be mapped to an OS task. If you don't map runnables to OS task, then the tool will throw error. And the process how it will be out, the RT will not be calling the runnable directly. RT will be monitoring the event. Once the event is happened, a flag will be set and it will call the OS task using activate task. That is each task will be associated with that event. So you will call that particular OS task, and all the runnables that are mapped under that OS task will be executed. Okay, so this is how your scheduling and your communication process will look like from a C code perspective. Okay, so the idea is the RTE is responsible for the entire scheduling and the establishing communication between the software components. So these are two major responsibilities of the runtime environment. Okay, some other things it also does is virtual function bus. It gives you communication APIs to communication between two software components. Three types of interfaces are there: AUTOSAR interface, standardized AUTOSAR interface. We have discussed about all those things. Excuse me, sorry. It also supports something called as I mean, scheduling is something that we have done. It also we've discussed. It also supports something called as portability. So what do I mean by portability is, let's say, for example, I've developed a software component which is like, say, built in for some other application. With AUTOSAR, the whole idea is you will be able to use the same software in your particular EC also. You'll be able to port it. Okay, so that portability will be very easy. Not just between for another application, it could be also for variants. That also is possible. Yeah, it will support multiple instantiation in the sense, let's say I have a particular function. Okay, let's say, for example, door status monitor. There is a particular runnable which is designed for the door status monitor. That runnable has a list of work. Okay, it will check the status of the sensor, do something, update something on the canvas, blah blah blah. It has so many works. Okay, now this runnable has to do the same work for both my left door as well as my right door. So what I can do is I can actually create instances of this runnable. Okay, so like say I will support multiple instances. So in that case, what happens is the same runnable I can like say use multiple. I can have multiple instances. So the idea is, if at all that runnable has to be called, then it will be called. But if both the runnables have to be executed at the same time, then it will copy that runnable into a separate memory location and execute it parallelly. So multiple instances will be like say multiple instantiation is being supported. Okay. So again, it will like say take care of interrupt management, and it will also do something called as data. It will handle data inconsistency. That means making sure it will have data. Your data will be like say consistent. Okay, so that is something that your RT will take care of. Okay, so in your sender receiver communication, we'll talk. We'll now break it into two parts. RT now. Till the time I mentioned, we will only first half of the session we will like say spend on communication between software components. How does your RTE establish communication between software components? So that is something that we can talk about. So there are two types of interfaces, like I said, sender receiver and client server. So sender receiver is used for to establish communication between two software components. Especially if you just want to like say pass data from one variable to another. This is a classic example of a sender receiver interface where we pass to the variable from one .c file to another .c file. This is how your code gets generated. You have some write APIs, you have some read APIs and all those things. So that's your sender receiver communication. In sender receiver communication, there are like say two interesting things that can happen: implicit communication and explicit communication. So implicit communication means what happens is when you read the data from the runtime environment. Okay, I'm talking about explicit communication. Okay, it just like say your software component will directly read the data from the RTE.c file. Okay, or it just reads the data directly from the RTE. So that way it is called as explicit communication. And in implicit communication, what the problem in explicit communication is, let's say, for example, two runnables are trying to access the variable at the same time, especially during, like, say, I will call it during preemption. Okay, during preemption, one runnable will be executing and it is modifying the data. and as and when it is modifying the data, let us say, for example, the variable is right now present in your CPU register. Okay, it is right now present in your CPU register, and this runnable is being preempted. And as it is being preempted by another higher priority runnable, what happens is that runnable will execute, and that variable will be now stored back into the location, in the memory location. When I say memory RAM, now after this preemption, what happens is the older runnable which was executing, he will start executing, and now he will replace it with a new value. So instead of getting one value, it now gets two in values. So this typically what we call it as data inconsistency. To avoid such data inconsistency, we need to kind of create different kinds of techniques are being provided in RTE. One technique is like, say, implicit and explicit communication. Where in implicit communication, I will buffer the runnable, and like say, I will like say, I will buffer the runnable, and I will take it from the buffer, process the data, reload it back into the buffer, and then send it back to the RTE. So that way, you will make sure that it is consistent. Explicit means you'll directly take it from the memory. When I say memory, it's the RAM. Okay, so you take it from the memory, process it, and send it back. So that way, what happens is it'll be faster. But the problem is data inconsistency could happen. Inconsistency challenges could pop out. So that's the difference between implicit and explicit communication. Then we have queued and lastest bit. Queued is where I will like say talk only about last is where I'll only talk about the last available value to take a decision. Queued, if I choose, then I will have a list of data. I have the history of the events. So you can use the history of the table and probably take some average from the history of the events and do some math and take it. So that and all can be like say done using your queued events. So both these types of variables are supports are being offered in RTE. Then in client server communication, we have synchronous and asynchronous communication. Synchronous is more of blocking, like what we call an embedded typically blocking function. You call another function, you expect the other function to return something. Okay, till that fellow returns something, you are waiting for that value to be returned. So that is called a synchronous or blocking function. Asynchronous is you call the other function and then you just keep going ahead with your task. As and when the other fellow returns some value, okay, then you kind of take that as an RTE event itself, and then you trigger the action. So that way, what happens is you will be able to, like say, make sure that precious resources are not blocked. Okay, so that's your synchronous and asynchronous functions, and client server communication is able to do it. So synchronous is a blocking function, asynchronous is a non-blocking function. If I have to put it into simple C terms, there is something called as mode communication. Modes are like say whenever there is wherever there is a change of mode that happens and your application software component needs to be communicated. Okay, the change of mode can be like say anything. It could be from no com to full com mode. That could be one change of mode, or it could be some production mode to like say run mode, or like that. It could be anything. Like that, if you have written some BSW rules, and when the BSW rule ever changes, and you have a new mode that is being moved for development, then I can use mode communication. Calibrations parameters, there is a separate entity. We have separate software components which are created in the application layer, managed for calibration. Okay, especially for sensor calibration, all those things we use calibration parameter communication. Okay. So the one thing that we need to understand and appreciate is client server communication and sender receiver communication can be used for inter-ECU communication. Okay, so they can be used for inter-ECU communication, whereas your mode and calibration parameters are all restricted to intra-ECU communication. So runnables, like I said, we can broadly categorize runnables into two types. One is asynchronous and synchronous. When I say synchronous, it's also called as category 2 runnables, which is nothing but a blocking function. Category 1 runnables or asynchronous functions are nothing but non-blocking functions where you don't have to be like say worried about waiting for the other function to return your value. You can just go. We just talked about implicit and explicit receive. Yeah, synchronous communication. We just talked about it. And asynchronous communication is something that we can talk about it. Okay, then I have communication between software components. Okay, so to establish communication between software components, excuse me, apart from using all these techniques, read, write, client server communication, mode interface, calibration interfaces are like say used for inter software component communication. Apart from inter software component communication, RTE is also responsible for intra software component communication and synchronization of runnable entities. Okay, like say for example, which runnable has to be executed on what time, all those synchronization has to be executed by the RTE only. Okay, so for this to support, RTE supports three major parameters. It's called inter-runnable variables, per instance memory, and there is also something called as an exclusive area. So what are these three items? Okay, so exclusive, we'll talk with exclusive areas. Okay, so what is an exclusive area? So let's say, for example, I have a particular runnable, and this particular runnable is trying to, like say, put some data into the EEPROM, okay, which we call it as NVRAM in our AUTOSAR. So let's say it is trying to access some variable from the NVRAM, or it is like try to write some data into the NVRAM and things like that. That's the purpose of this particular runnable. And I don't want this runnable to be preempted during the execution. Okay, during the execution, when this runnable is being called, whenever if I have a higher priority runnable that is like say triggered, then the probability is then the chances is that this particular runnable can be like say preempted. That means it will stop, it will be executing the other runnable, and then it will come back. So that time what happens is the data which was supposed to be saved can also be changed. Okay, so that way there is a lot of inconsistency, data inconsistency problems that can arise. In order to avoid it, what is the best way is I want this particular runnable not to be preempted. Okay, as it's being executed. Okay, so that is something that I can do. So that way, what happens is even if a higher priority task comes and tries to stop this runnable during execution, it will finish his work and then only like say do it. Okay, it's not for a task, it's for a runnable. Okay, so you can like say task, you can like say configure whether it is preemptive or not preemptive, but you cannot like say provide that kind of customization for a runnable. Okay, so you cannot say a runnable should be preempted, non-preempted, and all those things. Only the OS task you can do it. So, but here I want this runnable not to be preempted. So what I can do is I can map this runnable to an exclusive area. So whenever I map a runnable to this exclusive area, what it will do is it will know that okay, I can create one exclusive area. Okay, I can create one exclusive area and say only say 2 or 3 runnables can enter into this exclusive area. Okay. So the first way what it will do is it will know that only these 3 runnables can enter into the exclusive area. Second, all these 3 runnables, whenever they are execution, will not be able to, they will not be preempted by the OS task. Okay, they will not be preempted by the OS task. So that way, what happens is it will make sure that data consistency is available. There are many ways this exclusive area implementation can happen in the code level. One is say, for example, OS interrupt blocking, OS resources, OS pin lock. Okay, these are like the different techniques on how this inter-runnable variable can be executed in the can be executed in AUTOSAR. But generally, the idea of using a exclusive area is that the idea of creating an exclusive area is that you create an exclusive area and map runnables to the exclusive area. That runnable will not be preempted during its runtime or during its execution. Okay. So one method, I'll just to kind of give you an OS resource is a technique. So in that technique, if you look at it, what happens is the OS, when it is like say kind of scheduling, what it will do is it will raise the priority of this runnable over the priority of the runnable that is trying to, over the priority of the OS task which is trying to preempt it. That way, what happens is it will stop the resource from being allocated. It will finish this guy, and only then execute resources or say allocate resources for the next task. So there are say different techniques, but yeah, that's the general idea of our exclusive variable. We have something called as per instance memory. Okay, so this per instance memory is a very interesting feature. Okay, let us say, for example, I have multiple instances. I talked about this door monitoring, correct? So let's say, for example, the door monitoring system is being created, and I have multiple instances of this door monitoring that run over. Okay, one could be for front left door, another could be front right door, another could be rear left door, another could be rear right door. But what happens is I want some APIs, okay, which will access the particular instance. Okay, I want status of only the real. Okay. So like that, I want some particular APIs to access the status. Then what I do is I can use this per instance memory where it provides where it provides access to the specific instances of the memory. So that way you will be able to access that particular instance and derive data from whatever it is. Okay, so that's the whole idea of your per instance memory. Okay. Then there is something called as inter-runnable variable. Okay, so inter-runnable variables are nothing but how do we handle global variables? Okay, that's the basic idea of inter-runnable variables. So again, it is used for supporting multiple instances. Okay, idea is, let's say, for example, you have a particular variable, and that variable needs to be written into the RTE, or it needs to be handled at the RTE level immediately. Then I can use this API RT underscore IARV read, point out what is the particular instance of from which it is say taking, okay, and all those things can be done. Okay, so it will provide the current value of the interrunnable variable. Okay, it will provide the current value of the interrunnable variable. So interrunnable variable is nothing but your typically called as your global variable. In simple C terms, if I have to put it, okay, it's an equivalent of our global variable. How do I handle the interrunnable variable, especially if I have, say, multiple instances and all those things, is our idea. Okay, if you look at it, during the startup, when if I want to read the variable, okay, if your application software component wants to read what is the particular value immediately after startup, if you say try to do it, you will find that it will be say it will be loaded with the init value. Okay, it will be loaded with the init value. There is an important pivot to it. Okay, this function, okay, this particular function, okay, can be used inside the runnable of a software component, but we cannot use this run API in multiple runnables of the same software component. Usually, you want to access the variable, you want to access this global variable or interrunnable variable. You use this API and access it. Okay, but inside one software component, you should have only used it once. You cannot say use it under different runnables and do it. Okay, that way what happens is it will again create data inconsistency issues. So this is how you read it, and same thing holds good for write as well. There are say many types of access points and many types of communication paradigms that are available in RT. There's RT underscore read, there's RT underscore write, there's RT underscore IRV read, there's RT underscore IRV write, there is RT underscore I write, which is implicit write, there's RT underscore simple write. Okay, write means just write it explicit. Like that, there are different kinds of APIs and access points that are being provided by RTE for different applications, etc. Okay, and similarly, you have say APIs for client call, function call. You have say APIs for function definition. Sorry, you won't have access points for function definition, because function definition and function prototype will be the same format. But you'll have a function call for that. You will have say the API. All these APIs generated for establishing communication between software components. When I say software components, it could be an application software component or another application software component, or it could be an application software component or a BSW software component. In both the cases, you will find that these communication paradigms are very, very important, and these access points or APIs will be used to establish communication. No two software components can talk to each other directly without the RTE. Okay, all routing between application software component or another application software component has to go through the RTE only. Okay. Okay. The second, maybe the last point that I also wanted to mention is about the triggering of the runnables. Okay. So when I say triggering of the runnables, this is more to do with the scheduling. Okay. This is more to do with the scheduling. Okay. There are like say different types of RT events, which I have listed out on this picture. Okay. So based upon the happening of the RT event, a flag will be set. And once the flag will be set, the RT will call the OS task, and the OS task will execute all the runnables which are mapped under it. Okay, so that will be the process flow. So what are these RT events? Timing event. Okay, you can map a runnable to a timing event. Okay, so timing event means whenever there's 100 millisecond time elapsed, what happens is your timer will like say trigger one API, and that API will be used to set an RT event. And once this RT event flag is set, again, like I mentioned, we'll go call the OS task, and the OS task in turn will execute all the runnables mapped under it. Okay, so that's called as a timing event. Background event, okay, you can also map a runnable to a background event. Background event is like say if you have a runnable with very low priority, then what happens is you can map it to a background event. That means when no other resources like say are used, or it's like say completely available, your RT has enough resources, then it will execute these runnables. Otherwise, it will not execute this runnable. Data received event, when you receive an event in the RTE, let's say for example in our use case, we wrote something into RTE, right? The status of the light. So the second runnable in can be like say triggered on the RTE write itself. Okay, so like that you can like say set the trigger. Some errors when you like say send something and you get some errors, how do we handle it? That could be another point. Send complete, you transmit the data successfully. Your lower layer will return e underscore okay, telling your RTE that okay, your data has been successfully transmitted. This in turn can be used for the application for some decision making. Then we have something called write complete data event. We talked about it. Send and write are like synonymous. Okay. Then we have something called as operation invoked event. That's for a more client server call. So let's say, for example, you have a server runnable. Okay, what should be the trigger for the server runnable? When your client calls it. That's typically what we call it as operation invoked event. Okay. Asynchronous server called return point. This is like say your client has called the server, and what happens is it's not a synchronous function, it's an asynchronous function. That means he'll call and keep executing his job. Now your server is returning a value. Okay. Now on returning a value, you want to like say trigger that particular client or process the information from where it is left. Like that, you want to do something, then you like say set it as an asynchronous server call returns point. So that means the server will return a value which your client has asked for. Now your processor can start processing it again. Okay. Then there is something called a switched mode event. So that means these are mode of BSW managers, mode management. When you switch from one mode to another mode, you want a group of runnables to be triggered. So maybe in the production cycle, you want the runnables to be executed in a different way. In some other cycle, you want it to be different. All those things can be triggered in your, that can be mapped to your mode switch event. All right, so kind of high level, more things I've covered. Whatever I wanted to cover from a C coding perspective, covered. Any questions you want, I'll probably take it up. And then, yeah, I'll open up for questions, because I've already exceeded the time limit. Yeah, are there any questions? Hello? Am I audible? Hello?
Yes, Karthik, you are.
Yeah. Any questions, team?
Hello, Karthik. I have one question.
Yeah, Santosh.
Yeah, regarding this implementation part, right? So for the SWC, so we do implementation, right? So there, it's a part of data mapping. You said, as you said.
If you don't mind, can you be a little louder, Santosh? I'm not able to hear you.
Hello, is that clear now or still?
Yeah, better. Please go. Yeah.
Yeah. So it may be regarding the data mapping part actually. So we have something called application and implementation. So what's the basic difference between these two? Like, if you want to design a data type, so how can I go with an application or implementation? What is the criteria that I need to look for, like whether my data type should be application or implementation? And second thing is like what exactly this data mapping set is about.
Type mapping set. I think you're talking about type mapping set, not data mapping set. Correct?
Yeah, yes. So that is in the data type editor. We
Okay.
see
See,
like
okay. I get it. All right. So idea is, let us say, for example, you are like managing you're monitoring engine temperature. Let's assume. Okay. You're
okay,
monitoring engine temperature. All right. So this is your use case. Let's assume.
okay,
Now your application data type could be temperature, the physical quantity. Okay, the physical quantity that you are like say talking about. That is your application type. Okay, application data type. Implementation data type could be like say for example, something like I will call it engine temperature. Okay, it could be like say engine temperature. All right, where you are trying to say this is the data type that you'll actually see on your C code. That will be like say on your C code. The base data type, there's also something called as a base data type. Okay, so the
yeah,
base data type is the data type which is like say equivalent to your AUTOSAR data type. Okay, let's say for example UN16 or UN32 or anything like that. Okay, so idea is your application is mapped to implementation. Implementation will be mapped to your AUTOSAR data type or a base data type. Okay, in your C code, when you see it on the compiler, what you'll see is you'll always see only the implementation data type. Okay. So if you don't map it to an application data type, it's fine. Okay. If you don't write an application data type, as long as you keep it as a very simple, you just say engine temperature, that's the data type, and you map it to an AUTOSAR data type of say UN16. Okay, it should be good. Okay, you don't have to necessarily create an application data type. But your application data type is actually like say, for example, is talking about temperature. In temperature, you can like say have engine temperature, things like that. Okay, so you can like say be more precise in your implementation data type. So application is more your physical quantity. Implementation is more of your C perspective. Whatever you see in the compiler perspective, actually the microcontroller understandable data type is your AUTOSAR data type. Okay, and when you're talking about type mapping set, your application data type has to be mapped to your implementation data type, which in turn has to be mapped to your AUTOSAR data type. That's what we mean by data mapping, type mapping set.
okay. So here my question is like, if you consider any individual software component, so it is not mandatory that I need to have a data set there, right? If it is an only
You don't have to
implementation.
create some data type for individual software components. Data types could be generic,
Okay.
which can be shared between different software components. You can create data types and you can use it in different software components. Yes.
Okay. And how about this memory section that is we generally configure during the implementation under the implementation of the internal behavior?
Uh-huh. How about the memory?
Memory sections that we map, right, for this
Uh-huh.
under internal behavior.
Okay. So you mean the stack size? How do we allocate?
Yes.
Okay. See, the stack size allocation is like say specific project, specific thing. Okay. Usually, what happens is if you are having a compiler, the compiler should be able to kind of help you understand what is the stack size that is required for your particular runnables, all those things. So with that information, you will be able to compute the stack size and map it to a particular OS task. That will be the best way.
So it can be considered like the complete partition of the memory is taken care at the OS configuration level.
Yes, I mean it's not that it's not my duty. It is usually done at the stack size is the responsibility of like say allocating resources is at the OS level only. So I think it's better to keep it there rather than confusing it here.
Okay. Yeah. Thank you,
Okay.
Karthik. Thank you.
Yeah. Any other questions? All right. I think, I mean, if you at all you have any questions, please do write to us. We'll be happy to write back to you as well. Okay. And yeah, thank you so much for joining us on this occasion.